This video contains 3 examples of exponential functions from the Leaving Cert Higher Level course. And here's a couple of examples of exponential functions. It's exponential function if it takes the form to the power of x, some number to the power of x. Here we can see that there's maybe 2 main types of functions. There's increasing exponential functions. I marked this one in green, like 10 to the power of x. Or this second one, f of x, which is 2 to the power of x. They're increasing functions. Or it could either be decreasing functions. In this decreasing function we have 2 to the minus x, and this one here is 10 to the minus x. Example 1. A bacterial colony doubles every hour. If 10 bacterial cells were present at the start of an experiment, complete the following table. Well, we see at 0 hours there was 10 bacterial cells, and it doubles every hour, so that would be 20, 40, 80, 160 and 320. Now let's draw a graph of this. So in our graph we'll do the bacterial numbers and the hours, and we want to go up as far as 320 in terms of bacterial's numbers. So we'll use our space like this. And in hours we're going out to 5 hours, 0 to 5. And we just put our numbers in. We have 0, 10, 120, 240, 380, 4, 160 and 5, 320. And we join our curve. And that's what an exponential function might look like. I'll place that to the side. Now, question 3. How many would the population increase by in the 6th hour? Well, we know at 5 hours there's 320, and at 6 hours this would double, so that would give us 640, and the difference here would be the increase in the 6th hour. So the increase is obviously 320. Okay, question 4. What is the percentage increase in the population that occurred in the 6th hour? Now we know the actual increase is 320, and we're comparing it to the 1st hour. So we write it as a fraction of the 1st hour, so that's 320 over 10 compared with 10. And we multiply it by 100 and put a percentage symbol to turn this into a percentage increase. And this gives us 3,200%. And part 5, write an expression for the size of the population n after t hours. So we want this in terms of n and t. Well, term n of a geometric series is a or n minus 1. And this is geometric because we're doubling each term or multiplying by 2. So in other words, the common ratio is 2, and the first term we see is 10. A is equal to 10. And what is n? Well, n in terms of t, the first term is 0, the second term is 1, so n is t plus 1. So n, and the size of the population, is term n, and term n in terms of a, well, a is 10, r is 2, and then we have n is t plus 1, and then it's minus 1 following the formula. And obviously t plus 1 minus 1 is equal to t. So we have 10 bracket 2 to the power of t. And that's the answer. The graphs of 2 exponential functions, y is equal to capital A by small a to the power of x, are given in the diagram, and we're to find what capital A and small a are. Well, f of x is equal to capital A by small a to the power of x, but we know 2 input values. If we input 0, the output is 1. So in other words, capital A by small a to the power of 0, anything to the power of 0, well, is just 1. So that's capital A, and that's equal to the output value 1. So capital A is equal to 1. 1, 2 is also a point, so if we input 1, that's capital A by small a to the power of 1. Now, since capital A is 1, then we have small a to the power of 1. Well, anything to the power of 1 is itself, so that's just small a, and that's equal to the output value, which is 2. So small a is equal to 2. And therefore we have our function. So f of x is obviously equal to 2 to the power of x. Now in number 2, we do it the very same way. We know input and output values. So h of x is equal to capital A by small a to the power of x. If you input the value with output 0, with output 4, so input 0, that gives us capital A by small a to the power of 0, but anything to the power of 0 is 1, so that's just capital A. So capital A is equal to 4. So that's the first part of it. The second thing we see also that 1, 2 is a point. So if we input the point x equal to 1, the output is 2. Now we know capital A is 4, so that's 4 by a to the power of 1. Anything to the power of 1 is just itself, so that's just equal to 4a. And 4a is equal to output value, which is equal to 2. So in other words, 4a is equal to 2. Well, if 4a is equal to 2, we divide both sides by 4. So a is always 2 divided by 4, which is a half. So a is equal to a half. So we could rewrite h of x and putting in our values for capital A and small a, that it follows that h of x is equal to 4 by a half to the power of x. Now, half the power of x can be rewritten as 2 to the minus 1 times x, or just 2 to the minus x. Example 3. Given that the intensity of an earthquake is represented by the formula A is equal to 10 to the power of m, and the energy released during a quake is given by the formula E is equal to 10 to the power of 1.5 times n plus 4.8, where A is the amplitude and m is the magnitude on the Richter scale. We want to compare the intensity and the energy of an earthquake of magnitude 6.1 on the Richter scale with a quake of 4.7. Okay, the intensity we see in this here is the same as the amplitude, and that's given by the letter A. We want to compare the intensity. Now we know the magnitudes are 6.1 and 4.7. So the first magnitude is 6.1. So what's the amplitude of this, or the intensity? Well, that will be 10 to the power of 6.1. The second quake is 4.7. So the amplitude of this, or intensity, A2 we'll call it, is 10 to the power of 4.7. And we want to compare these. But compare means really what's the ratio of one is to the other. We could write them as a fraction or a ratio. So A1 is to A2. So we write A1 divided by A2. So we write this out as a fraction. Now the rules of indices say we subtract the dividing one. So this is 10.61 minus 4.7, which is 10 to the power of 1.4. And if you put this in a calculator, it's roughly equal to 25. So this tells us that A1 is to A2 is the ratio as 25 is to 1, or A1 is 25 times more intense. That's the first answer. The second answer is asking also to compare the energy. So this is asking, well, what's the energy of the first compared to the energy of the second? Again, as a ratio or a fraction. So this time we just sub in our magnitude values into the energy formula given here. So the values we're putting in are 6.1 and 4.7. So the energy of the first one, we're putting in, instead of m, the number 6.1. We just work out the power here. You can use the calculator if you want. And this is 10 all to the power of 13.95. The energy of the second one, this time we're putting in 4.7 instead of m. And working out the value of this power, it's 10 to the power of 11.85. And we write one as a ratio or a fraction. So E1 divided by E2. 1 over the other. Again, when we're dividing, what we're doing in terms of the powers or indices is we subtract the dividing indices. So this is 13.95 minus 11.85, which is 2.1. So 10 to the power 2.1, which is roughly equal to 126. Therefore, the energy of the first one compared to the energy of the second one is in a ratio of 126 is to 1.